Bruh. 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 Good morning, fellow mathematicians! Welcome back to another video. You might have seen it in the introduction. We are going to evaluate this crazy-ass series today. And no, I did not come up with this myself. I have to disappoint you, but Daddy Euler did. This Euleroid boy right here. I don't know how any mere human being can come up with something like this, but well, we are going to do it. And for this, we are going to take a look at Fourier series, Fourier-Reihen today. Yeah, that was the German word, Fourier-Reihe. And yeah, for this I would like to take a look at a certain function on a certain interval. It's a piecewise continuous function on the interval from -1 to 1, so keep this in mind. And the function we are going to construct ourselves is the following. F of x is going to be, well, a piecewise continuous function. Either, if we are on the positive somehow, we get that this is x minus x squared on the open interval from 0 to 1. Or we have that this is nothing but negative f of negative x on the interval from -1 to 0. Okay, this might seem really arbitrary, it is, but like many things in analysis, you have to construct yourself something to get things worked out. So yeah, that's the function we are going to deal with. I don't really know how it looks like, so it's supposed to look something like this, at least on the positive axis, but on the negative one, maybe something like this. I'm not really certain. Maybe someone can post a little Desmos graph or something down in the comments if you wish. So yeah, just for the people who like the visual approaches to shit right here. And yeah, like I said, we are going to take a look at this function on a certain interval, and it's quite obvious that our interval goes from -1 to 1. So our interval, where we have -L and L as the period, you could say, is going to be yeah, x element of -1 and 1, where our L is going to be 1 in this case, our period. And yeah, I did a little introduction to Fourier series using the Dirichlet-Kern and stuff like this. I solved the basic problem using this right here, based on the introduction by Black Pen Red Pen. So check that out if you wish. He made some videos on Fourier series. Okay, so now we have to talk about those Fourier coefficients right here. Let's start off with a naught over 2. A naught over 2, by definition, is going to be 1 over, in this case, L. 1 over 2 times L. I'm terribly sorry. I always have to think about it, but then I think about the Dirichlet-Kernel and I remember, 1 over 2 pi. Yeah, so this is 1 over L from -L to L of, well, our function integrated with respect to x. Okay, so you see we have this chunk right here, but I want you guys to notice something. We are working on a symmetric interval. If our function were odd, then that would completely vanish. An odd function integrated over a symmetric interval, well, it's going to just be 0. I made a proof on that. Check that out. Maybe link in the description, I really don't know. So let's check if our function is indeed odd. Well, for this we have to plug -x into f of x. So let's see. Let's take a look at f of -x. Well, by definition, -x is going to be a negative x value. And since we are on this interval, it's kind of between 0 and -1, meaning we have to take this part of our piecewise continuous function definition into account. Meaning, by this definition, we have to plug -x into here. So we are going to get -f of negative x. But negative times negative in any field is just positive. I made a proof on that. Take a look into the description, maybe there's a video on that. Meaning we are going to get -f of x. And that's absolutely fucking brilliant because, well, that's the definition of an odd function. If you plug -x into here, it's going to be negative the function itself. So that's Gucci, meaning this whole chunk is going to be 0. Now let's take a look at the cosine part right here, the superposition of our cosine waves. Meaning our Fourier coefficients, AKs, are of the form 1 over L times an integral from negative L to L of f of x, and then we have the cosine of, okay, now we have basically this argument right here, but our L, remember, is 1, so we are going to get k times pi times x. Same spiel for the other Fourier coefficients right here after that. Okay, we have this chunk integrated with respect to x, and I want you guys to notice cosine is an even function. F is an odd function. Odd function times even function, in the reals for example, is going to evaluate to an odd function overall. Just plug negative x into here and you see that this integrand is indeed odd. Meaning, once again, this is just going to be 0. So yeah, we have evaluated the first two Fourier coefficients, so this chunk is going to vanish and this, and now we have to deal with this one right here, and this is a little bit more work, that's why I'm doing it on the next chalkboard. Next up is the continuous superposition of sine waves, otherwise known as Burger King, right here. And like I said in the beginning, we are working on an interval from -1 to 1, meaning our L can safely be replaced by a 1, meaning we can get rid of this fraction right here a little bit. Also, this is going to evaluate to 1 right here. Our upper bound is 1 and our lower bound is -1, respectively. We are dealing with a piecewise continuous function. In terms of integrals, it's really easy to evaluate stuff like this most of the time. It's not like with differentiation. Integrating is calculating the measure. In a plane, it's just calculating the area. Meaning, if we have this function right here, for example, like I said, I don't know how it looks for sure. If we have this function right here, what we can do, we can at first evaluate the area under this curve right here, and then just add the area under this curve to it. Meaning, we are going to break this up into two parts. One, from -1 to 0, the integral, and then adding the integral, the area, from 0 to 1 to it. Meaning, we are going to end up with, at first, an integral running from -1 to 0 of f of x. In this interval, is by this definition negative f of -x. Sine k times pi times x integrated with respect to x. For the next part, we are going to add an integral from 0 to 1 to it. Of what? By this definition is x minus x squared times the sine of k times pi times x integrated with respect to x. Okay, coolio. After that, you can just break this integral up into two more integrals, basically, just using the linearity. One of x times the sine of blah blah blah, and then minus the integral of x squared times sine. I don't want to deal with that right now. At the moment, I would like to take a look at this integral right here. By doing a little change of variable, namely, we are going to say that we are going to transform -x to x. We are going to see what we get. So if we transform this right here, our upper and lower bounds are going to change in this way. If we plug -1 to here, our lower bound is going to be 1, our upper bound is going to be 0. Also, if we do this substitution, then we have negative dx being equal to the new dx dt, for example. You can replace this x by t. I really don't care, it's just a name. So this part right here is going to evaluate to dt. F of -x is going to be f of x. And then we have the sine of k times pi times -x. Okay, I hope you can see where this came from. Times dx. Sine is an odd function, meaning we can bring this negative sign to the outside. Okay? And then we can distribute negative sign into the upper and lower bounds right here to change the boundaries from 0 to 1 on this integral. And this might seem pretty familiar because this right here is nothing but this integral right here. Meaning, if we add this integral to it, we are going to end up with 2 times this quantity right here. So 2 times the integral from 0 to 1 of, okay, now we can break it up. Finally, this is x times the sine of k times pi times x integrated with respect to x minus 2 times the integral from 0 to 1 of x squared sine k times pi times x integrated with respect to x. And here is where a little mess is going to start because we have to do a lot of integration by parts. let's just take a look at one of those integrals after another. So the first one is going to be integral from 0 to 1 of x times the sine of k times pi times x integrated with respect to x. Integration by parts, you can also do this imaginary part stuff. So sine of k times pi times x is nothing but the imaginary part of e to the I times k times pi times x, blah blah blah. But I'm going to do it that way, because why the hell not? We have to do 2 iterations. Differentiating x is the easiest, 1 and 0 after that. Integrating the sine is also not too hard. Just drag down this argument right here. So sine integrates negative cosine, so we have negative 1 over k times pi times the cosine, k times pi times x. Integrating this, cosine integrated is nothing but sine, so this is going to give us negative 1 over k times pi, whole thing squared, or negative 1 over k squared times pi squared times sine of k times pi times x. All that's left to do is multiply this together and add the upper and lower bounds to it, leaving us with negative x over k times pi cosine k times pi times x from 0 to 1. And then negative and negative becomes positive, so positive 1 over k squared pi squared sine k times pi times x from 0 to 1. I want you guys to notice if we plug 0 into here, this is going to vanish just because of this x in the numerator. If we plug 0 into here, this is just going to vanish just because of the sine function right here. If we plug 1 into here, well, this is just going to evaluate to sine of k times pi. Sine of k times pi, well, it's periodic in pi right here or something like this. Anyways, it's going to be 0 all the time, so that's just simple analysis. You can do, just take a look at the graph of the sine. So this thing is going to vanish actually. If we plug 1 into here, this is the cosine of k times pi. So it's going to alternate between negative 1 and 1 all the time. So this is going to evaluate to negative 1 to the kth power. And also if we plug 1 into here, well, this is just going to be 1 in the end. So this integral overall evaluates to simply negative 1 to the kth power, or just negative 1 to the k plus 1 power, I really don't care, over k times pi. Okay, coolio, we have done that, and now we are left with this one right here. I don't think that I can fit it on this chalkboard yet again, so see you in a second. Just to shorten this video a little bit, it's pretty trivial and a little bit left as an exercise to the viewer to figure out the following steps right here, doing the integration by parts when dealing with this integral right here. So all that's really left to do is multiply this together, apply the upper and lower bounds, and then we're done. So yeah, let's plug this in. We're going to end up with, I'm going to put it here, so this is nothing but negative x squared over k times pi times the cosine of k times pi times x from 0 to 1. Also, we are going to have negative is positive, so positive 2 times x over k squared pi squared times the sine of k times pi times x from 0 to 1. And also this last part, positive 2 over k to the third power, pi to the third power, or cube, whatever you want to say, cosine of k times pi times x from 0 to 1. Okay, those are just side notes. Now let's take a look at what we are going to get actually. Okay, let's start off with this one right here because it's easy. If we plug 0 into here, well, it's just going to vanish. If we plug 1 into here, like I said, sine is kind of periodic in pi. I'm always forgetting what is periodic in, never mind. So anyways, this is going to vanish if you take a look at the graph once again. So easy peasy lemon squeezy. If we plug 0 into here, okay, that's going to vanish just because of this x squared. If we plug 1 into here, well, it's going to be negative 1 over k times pi, and also cosine of k times pi, we have talked about this before. This is just negative 1 to the kth power. I want you guys to notice that this is the same term that we had right here basically. So just keep this in mind. I wrote it out a little bit, and don't forget to add your factors of 2 and negative 2 in the end to this whole thing. Okay, what about this right here? If we plug 0 into here, this is going to be the cosine of 0, so this is 1. So in the second part of the integration we have negative 2 over k to the third power pi to the third power. If we plug 1 into here, well, this is cosine of k times pi. Once again, this is negative 1 to the kth power times 2 over k to the third power pi to the third power. Okay, coolio, we have done that, and now we can plug this chunk in this integral we had right here. So in this whole thing we had derived before. So we are going to get negative 1 to the kth power over k times pi. Also we have negative 2 over k to the third power pi to the third power plus 2 times negative 1 to the kth power over k to the third power pi to the third power. I want you guys to notice that if we multiply this by negative 2, those are just additive inverses from each other. So this is going to cancel out. This is pretty cool. Hey, this is pretty good. Also, negative 2, and we can bring this 2 to the outside to get a common factor of 4. Also, we can just bring those fractions together. Overall, what you can get, also you can turn this sign around, you are going to get that this is nothing but 4 times, okay, we have something over k to the third power, pi to the third power, and also we have a 1 up here, 1 minus negative 1 to the kth power. And this is what we get on this integral. Yeah, that looks quite weird. And now we have to plug this chunk into our Fourier series actually. And this right here should do the trick. This space should be more than enough. So f of x is now. So some Fourier coefficients actually cancel out. So we got rid of this stuff. We don't care about this anymore. All that's left is a sum running from 1 to infinity of this chunk. We can bring the 4 to the outside actually. Then we have 1 minus negative 1 to the kth power over k to the third power, pi to the third power, and this has been the sine part, basically the odd part in this Fourier series. So this is the sine of k times pi times x over L, but L is 1, so just k times pi times x. This is what we have right now. Now we can just choose some value of f of x right here, some x value that we plug into here out of our interval of validity. So just some value that we can take out of this interval from negative 1 to 1. And well, this function has been constructed pretty nicely. So why not choose, for example, 1/2? 1/2 is a positive value. So if we choose x equal to 1/2, it's going to be 1/2 minus 1/4 is going to give us 1/4 by this definition. So f of 1/2 is nothing but 1/4, like I said, and we can actually plug this chunk in here. So this is going to give us 4 times sum running from 1 to infinity. That's supposed to be a 4, not a k. I'm terribly sorry. Some things just look really alike on the chalkboard or when I'm writing. So we have 1 minus negative 1 to the kth power over k to the third power, pi to the third power. Plug 1/2 into here, so this is k times pi, sine of k times pi over 2. Okay, coolio. We can divide both sides by 4 because it's not equal to 0 to get 1/16 is equal to this right here. Okay? Is equal to this series but without the 4. Why not just write it out a little bit and see what we get? So if we plug 1 into here, this is going to give us negative 1 minus negative 1 is going to give us 2. Also, we can multiply both sides by pi to the third power. Why the hell not? I'm terribly sorry, yeah. This makes things a little bit easier. Just get all the constants to the outside. Yeah, let's multiply everything by pi to the third power. Then we have k to the third power, but k is 1. So this is going to give us 1 to the third power. I'm going to put it like this. Then we have sine of pi over 2. It's nothing but, well, 1. Okay, this stays as it is. Next part, k equals to 2. Negative 1 to an even power is just going to give us positive 1. 1 minus 1 is going to give us 0, so this next part is going to be 0. After that, we have k being equal to 3. We are going to get, okay, this is negative 1, it's going to give us 2 once again. Okay, then we have 3 to the third power sine of 3 pi over 2. Okay, this is going to give us -1. So I'm going to put negative sign right here. Next part, we have something even once again up here. So this is going to give us 0. You can easily observe that the next one is going to be positive 2. Okay, so every time we have 2 as a common factor up here, over 5 to the third power, plus 0, negative 2 over 7 to the third power, and so on. Okay? And yeah, now we can divide both sides by 2, because it's not equal to 0. And we get that pi to the third power over 32 is nothing but a sum running from, okay, you see we have 1 over 1 cubed, negative 1 over 3 cubed, negative 5 over 3 cubed, positive 5 over 3 cubed. No, positive 1 over 5 cubed. Oh goodness, I'm terribly sorry. What the hell am I saying? What I want to get at is that we have only odd integers down here. Okay, so we have something over 2k plus 1. We want to start at 1, meaning our k can run from 0 up to infinity, so I hope that's clear. And also up here it's alternating, -1 to the kth power. And this is it. Yeah, we are done. So there was a lot of work, there was a lot of stuff to remember. As always, I'm doing all of this out of my head. I don't really have any notes with me. I'm never going to film a video where I have to take a look at my notes. The only exception was the quantum mechanical harmonic oscillator. I mixed a little bit up with the ladder operators, but out of those 300 something videos, I never really looked at my notes for a video. So yeah, that's one of the things I want to keep. I hope you did enjoy this video. If you did, please like, subscribe, recommend channel if you like. This thing right here is absolutely amazing, and Daddy Euler derived it first. He's an absolute genius. I don't know how someone can come up with something like this. Never mind. You can support the channel by buying those teachers I created, or support the channel on Patreon. Take a look at my website, blah blah blah. If you enjoy those videos, feel free to share them and to subscribe to this channel. And up until next video, have an Euleroid day, my boys. See ya!